Double integrals are used to calculate the area of regions bounded by lines or curves in a two-dimensional plane. This assignment focuses on applying double integrals as the area of a region by determining the limits of integration and evaluating the integrals using both manual and simulation methods. For the simulation part, we chose MATLAB as our software tool. This is because MATLAB provides built-in functions for both numerical and symbolic integration. It also offers high accuracy and reliable results, which are suitable for engineering calculations. Additionally, MATLAB allows us to easily define integration limits and visualize the region using graphs.
Assalamualaikum, my name is Muhammad Azim Kabir Muhammadin and my matrix number is BEE2030. So today I will explain about manual calculation, which is question number 1A. The given region is bounded by the lines y equal to x, y equal to 2 minus x and y equal to 2. For the first, the lines are sketched on the xy plane to clearly identify the enclosed region. The points of intersection are found as follow: the lines y equal to x and y equal to 2 minus x intersect at 1, 1. The line y equal to 2 intersect at 2, 2, and the lines y equal to 2 minus x intersect at 0, 2. From the diagram, it is observed that x varies from 0 to 1, and for a fixed value for y varies from y equal to x to y equal to 2 minus x. The area of the region is obtained using the double integral, which is therefore area enclosed by the given lines is 1 square unit. So that's all for manual calculation. Thank you. So today I will explain about question 1A, which is we use a MATLAB to simulate the coding and get the graph. For the first, this MATLAB code is used to visual and calculate the area of region bounded by the lines y equal to x, y equal to 2 minus x and y equal to 2. First, the lower and upper boundary function are defined using animus function, which is where y equal to x as the lower limit and y equal to 2 minus x. So the upper limit of the region for a given value of the x. The boundary lines are then plot to clearly show the shape of the region. After that, the region of integration between x equal to 0 and x equal to 1 is shaded using the fill to command, which help in visualizing the exact area being calculated. So important things we unit to this MATLAB, which is intersection points such as 0, 2, this one 0, 2 and 1, 1, and the last 2, 2 upload to the highlight the corners of the bounded region. The area is computed using define the integration by integrate the difference between the upper and lower function 2 minus x. So over the interval from 0 to 1, MATLAB integral function evaluate this numerically and give the final area as 1. Finally, graph format operating such as label, title, legend and equal axis, scaling and grid are applied to improve clarity and presentation. So I will run this MATLAB. So we get the final answer area, which is 1, the same answer with manual calculation, and then we get the graph region bounded by y equal to x, y equal to 2 minus x and y equal to 2. So here we get the graph. So that's all for me. Thank you.
Hi, my name is Vignesh Somenghan, number matric CE240139. So my question is to find the area of a triangle with the vertices 0, 0, 3, 2, negative 2, 2. So the first step is to find sketch the triangle on xy plane according using the vertices given. So since this is So since the floor of the shape changes its slope at the origin x equals to 0, we need to split it into two subregions R1 and R2. So we have to sketch on the triangle R1 and R2 and find M using y equals to mx plus c for R1 and R2. Once we've done that for both regions, we can find the integrals. We can get the integrals for R1 and R2. So after getting the integrals for R1 and R2, by using the formula on the top right, which is the double integral dA plus double integral dA, the first double integral will be R1, second double integral will be R2. By using that formula, we can put in the values and find the answer, which will be 5 units square. So that's all for manual calculation. So now I'll be presenting the script for calculating area of double integration. So for my question, we are calculating the total area of a triangular region defined by three vertices, which is 0, 0, 3, 2 and negative 2, 2. So in the first section of our code, which is from line 3, this one to 11, this part, we initialize our symbolic variables x and y. We then define our boundaries, which is a left boundary y equals to negative 6, right boundary 2 over 3x, and top boundary which is y equals to 2. So the second part is the strategy of splitting the region. Because the floor of our shape changes its slope at the origin x equals to 0, we cannot calculate the area with single integral. We have to split it into two subregions, which will be R1 and R2. So for R1, which is the left side, okay, x goes from negative 2 to 0, so here it is, negative 2 to 0, and the height of the shape is bounded by the line y equals to negative x at the bottom and y equals to 2 at the top. So this is left, right, bottom to top. So for R2, which is the right side, x goes from 0 to 3, the height is bounded by y equals to 2 over 3x at the bottom and y equals to 2 at the top. So this one. So this is basically the description for this place. So the next part, which is integration logic, which will be in line 16 here until 22. Okay, so we perform the double integration from these lines 16 to 22. By integrating the constant 1 over dy and then dx, we effectively calculate the area. We do this for both sides and then sum them up in total area variable. So the comments then output these results here. These are the results to the comment window, converting the symbolic mat into readable text. So this fprint is basically to convert the symbolic mat into readable text and put it in command window here. So the next part, which is the final part, to ensure our mat matches the geometry, we plot the region. So the fill command in line 43 here, okay, is the most important visual aid because it shades the area between our calculated vertices in yellow with a 30% transparency, allowing us to see that the area we integrated is exactly the triangle we intended to measure. So the triangle we did was this. So this is 30% shaded yellow. So this is correct. Okay, so in conclusion, the final output gives us the exact area of both subsections and the total combined area, providing both a numerical answer and a visual proof of the region, which is here. The answers are in the comment. So that's all from me. Thank you.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Shazwan bin Muhammad Fairuz. My case number CE250010. So the question is line y equals to x, y equals to 3x, and x plus y equals to 4. So first of all, you need to sketch all the line, and as you can see, the line x plus y equals to 4 is intersect with the line y equals to 3x and y equals to x. And as you can see, that there is the region between all those lines. So to find the area of the region, we need to split the region into two areas by using vertical slice method. So you need to find the interval of x and y on both area, and then you complete the calculation for both double integral, and the answer will be 2.
Assalamualaikum, my name is Muhammad Shazwan bin Muhammad Fairuz. So this is the simulation part where I am using MATLAB. So here is the breakdown of how part of the code works. So firstly, I define the X and Y as a variable of X symbols. This allows the software to perform integration exactly like you do on paper, keeping the fraction and variable syntax rather than rounding them to decimals. The most critical part of the code is how it handles the changing upper boundary, because the top of the triangle switches from the line y equals to 3x to the line y equals to 4 minus x at x equals to 1. We can solve it with a single integral. So first we divide into two parts. So we need to find the lower and upper y. Calculate the area using the double integral. Area is the sum of first area. So the third part is the visualization. The code doesn't just calculate the number, it creates the plot to prove the calculation match the geometry. So we use the command plot, which is to draw the three boundaries line. Each line is assigned a specific color, which is red. R is red, B is blue, and G is green, and a name for the legend. The next command is using fill. This is the most helpful usual tool. It takes a vertices we calculate. We plot 0, 0, 1, 3, and 2, 2. And the color in the area between them, so you can see the exact what region was integrated. So the phase alpha, the command of phase alpha is sets the transparency of the shading. This allows you to see the grid lines through the colored area. When we run the simulation, so you can see area of part 1 is from the 0 to 1 is 1. Area of part 2, the second integral from 1 to 2 is also 2. So the total of the region is 2.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Shazwi Izani bin Harun Nizam. My matrix number is CE240114. In this slide, I will explain about question 1D, which is we need to find the area of the region R enclosed by three lines: y equal to x over 2, y equal to 2x, and x plus y equal to 3. Because the upper boundary of the region changed, we must split it into two sections, R1 and R2, to solve it using double integral. So firstly, we need to find the vertices of our triangle by solving simultaneous equation. So after that, we can get point A 1, 2, point B 2, 1. The origin 0, 0 is our third vertex with the two proportional lines meet. Next, we set up our double integral for two regions for R1 and R2. For R1, x range from 0 to 1 and y goes from x over 2 up to 2x. For R2, x range from 1 to 2 and y goes from x over 2 up to 3 minus x. We add these two integrals together to get the total area. Finally, we perform the integration with respect to y first, then x. And finally, everything this gives us 0.75 plus 0.75, resulting in a final total area of 1.5 units square.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Shazwi Izani bin Harun Nizam. My matrix numbers is CE240114. To begin our simulation for question 1D, we utilize the MATLAB symbolic math toolbox. By declaring sims x, y, we instruct MATLAB to perform exact algebraic manipulation rather than numerical estimation. And then we define our three boundary lines as symbolic expression. Line 1 represents the lower boundary y equal to x over 2. Line 2 and line 3 represent the upper boundaries y equal to 2x and y equal to 3 minus x. Setting this up as variables allow us to easily reference them within our integration function. The core logic of the code follows the type of region approach from our manual solution, because the upper limit of the region changed at x equal to 1. We use two separate int commands. For region R1, we next the integrals calculating x from 0 to 1 and y from x over 2 to 2x. For region R2, we compute the integrals x from 1 to 2, y from x over 2 to x minus x, to 3 minus x. In MATLAB, we handle the inner integration with respect to y first, then the outer with respect to x, like our manual calculation. And then we sum them to reach the final result of 1.5 unit square. To verify our boundaries, we implement a visualization block. We use linspace to generate a range of x values and plot the line to ensure they intersect at our calculated point at point A12 and point B21. To simulate the area we are calculating, we use the fill command by providing the vertices of our sub-region. MATLAB shade the areas, allowing us to visualize, confirm that the integration limit match the physical space enclosed by the line. Finally, the script uses fprint to display the result in the command window. By converting symbolic result to characters of numbers, the simulation provides a clear summary of the intersection point derived, the individual area of each sub-region, and the total area of region R. So, if we run the coding simulation, we get intersection point at point A is 1, 2, and intersection point at point B 2, 1. Area of R1 is 3 over 4, area of R2 is 3 over 4, and total area of region is R equal to 3 over 2 unit square.
The coding simulation calculation for question 1D also generate a graph for this question.
In conclusion, double integrals are an effective and reliable method for calculating the area of regions bounded by given equations. Through this assignment, the regions were successfully analyzed, sketched, and evaluated using appropriate limits of integration. From the results obtained, we observed that the values from the manual calculation and the simulation calculation are consistent. This confirms that our manual solution is accurate and correctly verified using simulation tools.